So, the next module is module 4, in which we are going to look at again colloidal interactions, but looking at what is called as electrostatic interactions. They are also called as electrical double layer interactions. Okay, that is what we are going to do it for the next few lectures. That is going to be the contents. Okay. We will start with one by one. Okay. Today we will most likely look at the importance of electrostatic effects and origin of charges at the surface of particles, and if we have some time we will also try and look at models for electrical double layer. So, coming to the importance of electrostatic effects. Okay. Any thoughts? Why is there a need to look at electrical double layer interactions or electrostatic effects in dispersions? Some thoughts?
So, due to surface charges there will be some attraction or repulsion.
Correct, right. So, due to some surface charges there can be attraction or repulsion, right. So, it turns out that these interactions are very important, okay, because one of the example could be the stability of a variety of colloids, okay, be it food colloids. You look at colloids which are found in pharmaceutical dispersion, paint, okay, as well as waste water may have lot of contaminants which will have the colloidal dimension length scale, and the stability of all such things are affected by the surface charge on the particles. Okay. So, this is an example of a stable system, okay, unstable system. Okay. So, if you want to think about having a stable colloidal system, one of the ways of achieving that would be by incorporating charge on the particle surface. Okay. So, that is one example. So, the electrostatic forces also play an important role in the conformation and structure of macromolecules. Okay. So, if you look at several charge systems, okay, that is polyelectrolytes, okay, which are charged polymers, okay, or you could have polymers, okay, with ions adsorbed onto the surface, okay, or you could have proteins, okay, which are charged, and the kind of conformation that they take in solution, that means whether they would be in a extended configuration or they would coil up. Okay. So, that is determined by the surface charge that these molecules may have. Okay. So, therefore, there is a lot of interest to look at electrostatic effects in charged polymers and charged proteins, with an intention of understanding what is the structure of these macromolecules or structure of these entities when you put them in solution. That is one another reason to look at charge effects in these systems. Third is, if you look at people use a lot of virus particles as model systems, right. In the initial classes we talked about FD virus, TME, okay, particles like this. Now, so these virus essentially is made by the self assembly of large number of molecules, okay, and so basically the neighboring molecules, okay, from which the virus are made of, they are actually held together by electrostatic interactions. Okay. So, that means the electrostatic interaction between the molecules of adjacent layers in a virus are held together because of the electrostatic interactions between between the molecules that make up these virus particles. The other examples could be that if you look at measuring rheology, okay, or the flow behavior of solutions, or flow behavior of multi-component mixtures. If it has like say polymers or charged colloids, it has been found that the transport properties such as viscosity is indeed affected by whether you have a dispersion with charged particles or uncharged particles. Okay, people talk about what is called as a electroviscous effect, in which we can one studies what is the contribution of the charges of the particles to the viscosity of the dispersions. Okay. And finally, people also use particles dispersed, the charged particles dispersed in a medium, and you can actually manipulate the spatial organization of particles. So, if I have like say a container, okay, and say that they have charged particles. Okay. Now, when you are trying to use such a system for display applications, what you should be able to do, or you should have a control about the way the particles organize in the solution, right. Okay, that will lead to a definite display that one wants. Okay. And one of the way to do that would be that I take this dispersion and apply an electric field. Okay. Thereby, I can modulate the spatial organization of particles in the solution. Okay. So, therefore, in electrophoretic display panels, okay, one uses charged particles, and I can control their organization by applying an electric field. Therefore, there is also a lot of interest to understand such phenomena. How do charged particles behave in an electric field? What leads to the changes in the display behavior? Okay, so problems like that. Okay, so that's to tell you that there are various fields, okay, or there are various reasons why one could be looking at charge effects. If you come to the origin of charges, we have discussed this in the initial stages. Okay, people typically talk about 4 different mechanisms by which the particles can acquire charge: preferential adsorption of ions, adsorption of ionic surfactants, okay, both cationic and anionic, and adsorption of charged polymers. The 4th mechanism is dissociation of surface charges, right. We have talked about these things. So, if I say that I have a particle which has COOH group, if I put them in water, what will happen is you have COO minus plus 2H plus, right. So, that is a dissociation of the surface charge is leading to the charges on the particle surface, right. Similarly, we looked at adsorption of maybe H plus ions or adsorption of OH minus ions can make either a particle positively charged or a negatively charged. Similarly, I could have a case where I have a particle, and then if I add a charged surfactant, okay, it could go and sit onto the particle surface, okay, and I could either acquire a positive or a negative charge depending upon whether you are working with a cationic surfactant or an anionic surfactant. Similarly, the charged polymer can also go and sit on the particle surface and then make the surface either positively or negatively charged, right. We have discussed this already earlier, so it's just I am just trying to quickly. Now, when you have charged particles in a medium, so what is depicted here is a particle which is negatively charged and particle that is positively charged, and you can think about this could be a dispersion medium, right, or a solvent or a continuous medium. Okay. So, do you think this is a correct picture? So, if one asks you to imagine charged particles in a fluid, okay, do you think this is a correct picture? Maybe, somebody says maybe. Yes, somebody says yes. I would say no. The correct picture is this, right. You should imagine that you have charges on the particle surface, plus you also have, so the system as a whole has to be electrically neutral, right. So, if you take solution, the total number of positive ions or positive charges should be equal to the total number of negative ions in the solution, right. So, if you take a charge stabilized dispersion, if I count, the total number of positive charges should be equal to the total number of negative charges, right. Okay. So, people talk about two terms, okay, which you should remember, something called a co-ion and a counter ion. Okay. So, co-ions are the ions which have the same polarity as the charges on the particle surface. So, if I have, in this case I have a particle which is negatively charged. Okay. If I put in like say NaCl into the system, I am going to have Na plus and Cl minus. Okay. Cl minus, the Cl minus has a same polarity as the charges on the particle surface. Therefore, in this example co-ions is going to be Cl minus. Right. In this case the co-ion is going to be Cl minus, and counter ion are the charges, counter ions are the charges which have a charge which is opposite to the polarity on the particle surface. Okay. In this case Na plus, which comes from the NaCl that I have added, plus also the other ions that come because of the dissociation, both of them are counter ions in this case. Okay. So, therefore, whenever you talk about charged particles in a medium, you should there will be co-ions and the counter ions, which respectively are the charges which have the same polarity as the particles as the charge on the particle surface, and the of opposite polarity as what is there on the particle surface. Okay. If you look at literature, it turns out that so I said this is a charge stable charge dispersion and it is a medium, right. Now, if you look at all the body of work that has gone in Colloids literature on charged particles in a fluid, it turns out that in most cases electrostatic interactions have been studied in aqueous system, okay, or aqueous medium, and you will see very little work, okay, on of course there is a body of work, but you will not see much literature, okay, on studying electrostatics in organic medium. Okay. Although it is possible to design particles that have charges when you put them in organic solvents, if you look at the bulk of the work has been done using aqueous medium as a continuous phase, as compared to organic medium. Okay. That's the point that I wanted to make. Briefly I want to mention electrical double layer. What is electrical double layer? This is going to be important because we are going to talk about this for several lectures in the next few weeks or so. Okay. So, whenever you have charges on a particle surface, that is what is depicted here, right. This is charges on the particle surface. Okay. The surface charge on the particle surface causes an electric field, right. So, whenever you have a point charge, okay, we know that if I look at think about at any particular location E, right, at any particular location I can calculate what is the electric field, right. So, it is given by a simple, so if F is q1 q2 divided by 4 pi epsilon naught epsilon r, okay, if that is the Coulomb's law, right, r square, right. So, F is equal to q1 q2 divided by 4 pi epsilon r square. If that is the force between the two charges, now if I ask a question as to at a distance r from q1, okay, what is the electric field, is actually given by F by q, right. If let's say that I take a simple case where I have two equal charges, okay, and if I want to ask a question as to at any location at a distance r, from this charge, okay, the electric field is given by E is F by Q, right, and this electric field that is generated because of the charges on the particle surface, what it will do is it will attract the counter ions, okay, it will attract the counter ions. Therefore, if you look at this picture, so there is a layer of charges on the particle surface. In the immediate vicinity, there is a layer of counter ions, okay, and these counter ions are attracted to the charges on the particle surface because of the electric field that is created because of the charges on the particle surface. Okay. So, therefore, there is a layer of ions on the particle surface and there is a layer of ions, okay, in the immediate vicinity of the charge surface. So, these two layers of charges put together, they are what are called as electrical double layer. Okay. The layer of surface charge and the counter ions in the solution, that is what is called as a electrical double layer, right.